Hi, this is the video lecture for Calculus 1. So in this video, we are going to discuss further applications of integrals. There will be 3 applications for this video. In the first one, we're going to go to talk about arc length of curves. And in the second, we're going to talk about integral of volume by integral of cross-section formula. This is about volume. And the third application is volume of solid by dish or washer method. Okay, so for the first application, arc length of curves, so we are going to find the length of a curve y equal to fx from x equal to a to xb, and the formula we're going to go to use is the length is equal to integrate from a to b of square root 1 plus f prime x square dx, or equivalently the arc length L is also written as integrate from a to b of the square root 1 plus y prime square dx. So how we get this formula? So the idea goes back to the concept at the beginning of integral. So let's say this is the blue one is the curve y equal to fx, and then we divide the x variable from a to b into smaller subintervals, and then looking at on each subinterval, let's say at from xi minus 1 to xi, then on this subinterval the curve on this interval is approximated by straight line segment from pi minus 1 to pi. So we are going to approximate the length of the blue curve by the length of the straight line segment, and that we're gonna go to we are going to use the Pythagoras formula. So we're gonna go to form a right triangle here, and then this is the delta x and this is the delta y, right? And from the figure, as I said, so we are going to approximate the small arc length by the length pi minus 1 to pi, and then by Pythagoras, this is equal to square root of delta x squared plus delta y squared, right? This is delta x and this is delta y, right? And then we're gonna go to use linear approximation that we learned before, which implies that the delta y gonna be approximated by f prime at sample point xi star, where the xi star is any point on the interval. So this is xi star, okay? So plugging the approximate delta y with the f prime xi star times delta x, we're gonna go to get delta L approximated by square root of delta x squared plus f prime xi star times delta x squared, and then taking the delta x squared together with the square root, we're gonna bring it outside to be delta x, then multiply square root of 1 plus f prime xi star square, and then by summing, we're gonna get the length, the arc length approximated by sigma I from 1 to n of square root of 1 plus f prime xi star square times delta x, and then when we take n to infinity, as we learned in the concept at the beginning of integral, the summation gonna becomes integral, right, from a to b, and the function square root 1 plus f prime xi star square gonna become square root of 1 plus f prime x square, and the delta x become dx. So that's the explanation of the Arclength formula. Okay, so let's take a look at examples. Our first example, we're gonna go to find the length of the curve y equal to 1 plus 6x to the power 3 over 2, where x from 0 to 1. Okay, so by the formula, we're gonna need to find the f prime x. So this is fx, or we're gonna go to find y prime, right? The same thing. So let me written as y prime. So y prime is divided by the x, and by the formula, we're gonna go to d by dx of 1 plus 6 times x to the 3 over 2, and then we differentiate. 1 is constant, so d by dx is 0, and d by dx of 6x times x to the power 3 over 2 is 6 times 3 over 2 x to the 3 over 2 minus 1, which is equal to 9x to the 1/2, right? And then we're gonna go to calculate square root of 1 plus y prime square, which is equal to square root of 1 plus 9x to the 1/2 square, and this is equal to square root of 1 plus 81x, right? Okay, so now we can calculate the arc length out to be integral from 0 to 1 of the square root of 1 plus 81x dx. Then we make a change of variable, so let's 1 plus 81x to be u, which means dx gonna be equal to du over 81, and then we can get integral to be square root of u du over 81, and when x equal to 0, u equal to 1. When x equal to 1, u equal to 82. Okay, so by taking the 1 over 81, then integrate square root, we're gonna get 2 u to the we're gonna get the u to the 3 over 2 divided by 3 over 2, and then plugging u equal to 82 and u equal to 1, and do a subtraction, and that's just 2 over 243 and times 82 to the power 3 over 2 minus 1. Okay, so that's the arc length. Okay, so let's do another example. Find the arc length of the curve y equal to x to the power 3 divided by 3 plus 1 over 4x, where x from 1 to 2. Okay, so by the formula, we're gonna go to differentiate y, which is d by dx of x to the power 3 divided by 3 plus 1 over 4x, and this is by d by dx formula, it is x squared for the first term and minus 1 over 4x squared for the second term, right? And then we calculate y prime square. So that's x squared minus 1 over 4x square, and this is x to the power 4 minus 2x squared times 1 over 4x squared, and plus 1 over 4x square, and it is equal to x to the power 4 minus 1 over 2, right? And then plus 1 over 4x square, and then when we plus 1, the 1 plus y prime square, it's gonna take 1 to subtract 1/2. That's gonna go to be plus 1/2, right? And then plus 1 over 4x square. And observe that this is precisely equal to x squared plus 1 over 4x square, right? So when you take square root of the 1 plus y prime square, it's going to be x squared plus 1 over 4x squared. And then we can go to calculate the arc length by integration. So it is integrate from 1 to 2 of the x squared plus 1 over 4x squared dx, and this is x to the power 3 divided by 3 minus 1 over 4x, and then we sub x equal to 2 and x equal to 1 and do the subtraction. So this is just 8 over 3 minus 1 over 8. This is a substitution, x equal to 2, and subtract sub x equal to 1, so it is 1/3 over minus 1 over 4. So by calculation, we're going to have 7 over 3, and then plus 1 over 8. Okay, so next topic, we're going to go to see another application of integrals. In the second application, we're going to go to talk about a volume of solid. And the solid we're going to consider in this application is a solid S whose cross section at any let's say at any x perpendicular to x-axis has area AX. So according to the figure, so we suppose the solid is with the x-axis and y-axis, and when we take a plane, so this is in 3D, we take a plane perpendicular to the x-axis. This is the plane. Okay, this is the plane, and we perpendicular to the x-axis, and suppose the cross section of the plane with the solid is as shown, and suppose we can calculate the area at each x. So this is at the point x, at the number x here. X go from A to the B. At A is kind of like the leftmost of the solid, and B is the rightmost of the solid. So we cut the solid at any number x, and suppose the cross section, we can calculate the area to be equal to a function AX. Okay, then what we're gonna be use is the volume of the solid S is given by V equal to integral A to B of the cross section AX and integrate dx, and this is called integral of cross sections formula. Okay, so the reasoning behind this formula is as follows. So we do like before. That means we're gonna go to divide AB into sub-intervals equally, right? And then on each sub-interval, let's say from xi minus 1 to xi, the solid gonna be cut into a smaller solid, let's say Si. So this solid gonna be, instead of having a curve boundary, we're gonna go to look at uniform boundary. That means we're gonna go to take a point xi star in between, and then calculate the area A xi star, then we consider the approximate solid with the same cross section. So it means that this smaller approximated solid gonna have area axi star times delta x, right? So this is called delta v. Well, the delta v is approximated by axi star times delta x, and then we take the sum to get the total volume approximated by sigma I from 1 to n of the product of cross-section area axi star multiply the width delta x. So this is the width delta x, right? And then as n to infinity, according to our study of integral at the beginning, the sigma gonna becomes integrate from a to b, and the function axi star gonna becomes ax, delta x gonna becomes dx, and this is the explanation of the volume by integral of cross-section formulas. Okay. There is an alternative. If in the case that the cross-section we are not taking we are not taking perpendicular to the x-axis. Previously we are taking cross-section along x-axis, right? And we get cross-section ax at any x. But suppose now that we can go to take cross-section along y-axis at any number y and calculate the cross-section to have area ay instead of area ax. So it can be proved that if y goes from c to d, the volume of the solid gonna be integrate from c to d of ay dy, right? Compared with the previous one, from a to b, the area is calculated by integrate ax dx, but now the volume is integrate of area ay from c to d dy. Okay. So let me take a look at examples. Our first example, we are going to consider a solid with a circular base of radius 1. So it means that when you viewing from above, looking at the solid from above, you're going to see a circle, right? You're going to see a circle in the xy plane, circle of radius 1. Okay, radius 1. And then for this solid, when we take a cross section perpendicular to the base, it is equilateral triangles. So in this case, let us put the x-axis and the y-axis, and suppose we are making perpendicular to the x-axis, and it is said that the solid has the cross-section according to the figure. It is a triangle A, B, and C, where this is equilateral, meaning that the length of the triangle side lengths are equal, right? So we're gonna go to find, so let's say this is at x, we're gonna need to find cross-section area at x for this equilateral triangle. Okay, so according to this description, it means that when I cut the solid, then I look at the base, so it cut at x, number x, so we're gonna see one side. This is actually the side AB, right, in the figure. The x gonna goes from -1 to the 1, right? So this is our number AB to be integrated. Okay, so now at any x, recall formula for area of equilateral triangle. For equilateral triangle that has length A, side length A, the area is square root 3 over 4 multiply A squared. This is the formula we're going to use. So what we're going to need to do is now calculate AB, right? We're going to need to calculate the length AB. And here, because it is at x, so we're going to have 2 points, the point A and the point B. AB are on triangle, so it is equation x squared plus y squared equal to 1, right? Equal to 1. So the AB is going to be equal to 2y, right? And the y is just square root of 1 minus x squared, right? Because of equation for x and y. Yeah, so now I take y to be coordinate of the point B, x, y. The point A gonna has coordinate x negative y. Okay, so y is positive, negative y is negative, and then we according to the figure. So the area at x is the area of equilateral triangle. So we now know the side length AB, so the area is square root 3 over 4 multiply 2 square root 1 minus x squared and square, and this is just square root 3 over 4 multiply 4 and multiply 1 minus x squared, so it is square root 3 times 1 minus x squared. Okay, so now we know the cross-section area. Now the volume is by integral of cross-section formula, so we're going to go to integrate from -1 to the 1 of the square root 3 times 1 minus x squared dx, and by moving the square root 3, then integrate 1 minus x squared, we can have x minus x to the power 3 divided by 3, and substitute 1 and minus 1. So when substitute 1, you're gonna have 1 minus 1/3. When substitute -1, we can have -1 plus 1/3. So this is just square root 3 times 2 over 3, and then minus plus. So we're gonna go to 4 over 3, and the answer is 4 over square root of 3, right? Okay, so let me do one more example. In this example, we're gonna go to find the value of the solid S, whose base is the region bounded by 3x equal to square root of 36 minus 4y squared, and the y-axis and the cross sections perpendicular to the x-axis are isosceles right triangles with hypotenuse in the base. What do we mean here is that first let's take a look at the curve 3x equal to square root 36 minus 4y squared. This is by squaring both sides. You're going to see the equation 3x squared equal to 36 minus 4y squared, and this is just x squared over 4 plus y squared over 9 equal to 1, and it is ellipse. So you can sketch, but this ellipse is just half because it is required by the equation that 3x is positive, right? X has to be bigger than or equal to 0, so it is half the ellipse. and you can sketch this ellipse. It's gonna have minus 2 plus 2 x squared over 4 plus y squared over 9 equal to 1, and this is gonna be 3, and they're gonna be negative 3, and only half where x is positive. Okay, so this is a graph of 3x equal to square root 36 minus 4y squared, and another side, the region is also bounded by the y-axis, so meaning that you're going to see the region to be this part, right? This is the region, and then it describes that the solid has the cross sections perpendicular to the x-axis are isosceles right triangles with hypotenuse in the base. So it meaning that when I take x, any x, and then we draw cross section. Okay, so we're gonna go to we don't need negative 2, we're gonna need 0. Okay, and then looking at in 3D. Okay, so in 3D, you're going to see at X a right triangle cross section. And the figure shows isosceles right triangle with the hypotenuse at the base. So let me call A, B, and C. So on the left, we're going to see A here and B there. Okay, and AB is the hypotenuse. Okay, so this is at X, and this is at Y coordinate. Okay, yeah, so what about the well, there is another given formula that the area of isosceles right triangle with hypotenuse C as area A calculated from 1/4 C squared. So we're gonna go to use this. It means that I'm gonna need to calculate, let's say this is C. Once we know C, which is just AB, we're gonna be able to calculate the cross-section area. AX gonna be 1/4 multiplied C squared, right? So we're gonna go to looking at the point A and the point B. A and B are on the equation x squared over 4 plus y squared over 9 equal to 1. So it's gonna have x and then y positive and x with the y negative for the A. And for y positive, you're going to be able to calculate y from 9 times 1 minus x squared over 4, and then take the square root, positive square root, right? So this is the y, and c equal to ab is just 2y. And then you can see that the sorry, not a just 2y, so it's gonna go to be just y squared, right? Which is 9 times 1 minus x squared over 4. Okay, so now we can integrate to get the value. The value is integrate from 0 to the 2, right? 0 is the start, 2 is the stop, and then integrate the cross-section area, which is 9 times 1 minus x squared over 4 and dx. So we're going to go to get integrate by multiply out. Integrate 9 is 9 times x minus the 9 over 4 x to the power 3 divided by 3, and then substitute 2 and 0. So we're going to go to get 18 minus 3 over 4 and 8 minus 6, so that is 12. Our third application for this video is volume of solids that obtained by revolving a region about an axis. So we're gonna go to talk about calculation using the so-called disk or washer method. Okay, so let me describe what we're gonna do. We're gonna go to consider a solid S, which is obtained by revolving a region in the xy plane, region in xy plane about an the x-axis or a line parallel to x-axis. Okay, so for example, in this figure we choose the blue region here, the region, and then we are going to rotate this region about the x-axis. So on the right figure you can see that the rotation gonna give a solid, right? And then we are looking at the cross section, so we choose at x, and then we get this is the vertical line because we are going to make the perpendicular to x-axis, right? And this this vertical line, when you rotate, it's gonna give a disk in this figure, right? But take a look at another region. In this region, it is bounded by a straight line and a parabola, and it is also given by blue region. And we do the same thing. We are going to rotate about the x-axis, and the figure for the solid is on the right hand side. But if you look at the cross section, when you choose at any x here, so they're gonna be because the region is the region is above, so it's gonna give this line, and when you rotate, it's gonna give kind of like a washer, right? Washer. There's a hole inside. This is a washer. Okay. So in conclusion, when you rotate the area, when we rotate a region about x-axis, the cross section that you make perpendicular to the rotation axis is either a disk or a washer, right? So the rotation axis is x. We rotate about x. Okay, so cross section is either you get kind of like a disk in 3D, or when you rotate about x, you get not a disk but instead a washer. Kind of like this. So it means that the cross-section area calculation gonna come from either area of the disk or area of washer. So we're gonna go to use the cross-section area formula. It's gonna be either A for the disk, a dx is pi times radius at x square. Okay, so it means that when you have you know that the cross section is at x, cross section is a disk. Then you have at x, you're gonna need to calculate the radius r at x. Once you know the radius, you can calculate the area of the cross section by formula pi r square. So it is pi r x square. On the other hand, if the cross section is a washer, so they're gonna be outer radius, like larger radius and inner radius, right? So the smaller radius is denoted by rx, while the larger radius is denoted by capital Rx. Okay, so the area of washer is just, you just subtract bigger area to the smaller area, right? Which is pi capital Rx squared minus smaller Rx squared. Okay, so this is the two formula we're going to use. So once you have the formula for the cross section, you just go to integrate, right? That means that if we know the regions has x from a to the b, then we're going to employ the integral cross section formula for the volume to obtain volume in the disk. If the cross section all along is this, is integrate a to b pi Rx squared dx. But if the cross section is washer, the volume washer is integrate a to b of pi Rx squared minus r small Rx squared. Okay, so let's do examples. In the first example, we're going to go to find the volume of solid obtained by rotating the region bounded by the curve y equal to 1 minus x squared and the line y equal to 0 about the x-axis. Okay, so let's sketch the region first. Y equal to 1 minus x squared is a parabola, right? So the graph is when x is 0, it is 1, and when x is minus 1 or x is 1, y is equal to 0. So this is the parabola that's gonna go downward. Okay, and the line y equal to 0 is just the x-axis, right? So it means that the region we are looking at is this region. Okay, and the rotation axis is the x-axis. So what about the cross-section area? So we're going to choose at any x. So let's say this is at x, and then we're going to have, this is the line the cross section, right? When you follow the rotation, you're going to give a this, right? Okay, so it means that we're going to need to find out the Rx, which by the formula, it is just the distance of this point. So let's say this is A, we're going to have coordinate x and y, right? But the y is the y from the formula for the curve. So it means that the Rx is equal to y, and it is equal to 1 minus x squared for each x. Okay, so this is the radius. Then we follow the volume of the disk, volume for rotation when you have cross section to be this. Integrate from, okay, so this go from -1 to the 1, so integrate from -1 to 1 of the pi multiply Rx squared, so it is 1 minus x squared and dx, right? So we integrate from -1 to 1, and then I expand the 1 minus x squared to get 1 minus 2x squared plus x to the power 4 and dx, and then we integrate to get x minus 2x to the power 3 divided by 3 plus x to the power 5 divided by 5, and then plug 1 and -1. That's gonna give pi, when plug 1, gonna have 1 minus 2 over 3 plus 1 over 5, and when plug -1, you're gonna keep -1 and plus 2 over 3 minus 1 over 5. So eventually you're gonna see value to be some number. Okay. Okay, so next example, we're gonna go to find volume of solid obtained by rotating the region bounded by the curve y equal to x squared and x equal to y squared about the line y equal to 1. Okay, so first let me observe that we are no longer rotate about x-axis, but instead rotate about the line parallel to the x-axis, right? So y equal to 1 is just here. This is y equal to 1. So it intersect at 1. Okay, so we are going to rotate about this line. And what about the region? So by the description, it means that we're gonna go to sketch the y equal to x squared. This is the well-known parabola up. X equal to y squared is parabola going to the right. So from the figure, it means that the region is just here, here. And it is not difficult to find the intersection. Okay, intersection occur at x equal to 1 and y equal to 1. Okay, so now what about the rotation axis? Rotation axis y equal to 1 is precisely this line, right? It passed through the intersection point. This is y equal to 1, so we are going to rotate about this. Okay, so when you look at each x, okay, so you can see that x gonna go from 0 to the 1. When look at it, each x, and the cross section to the region gonna give this line, vertical line. And when you follow the rotation axis, you're gonna see a washer. Watcher. I no longer need this, so let me erase. We're gonna see a watcher. This is from, okay, so, and then to calculate the area, you're gonna need to have outer and inner radius. So the figure is not quite good. Let me erase something a little bit to make it more clearly seen. Okay, so let's say this is sorry. Okay, so okay, so the the small r is here. The figure is too small, and the bigger r is this rx. So what we're gonna need to know is small rx let me use the clean. This is the small rx, okay, while the big rx is from, okay, same as this distance. Okay, so I'm gonna go to calculate small rx. I'm gonna need to subtract, well, when you have two a straight line, vertical straight line, let me make the blue line longer. So when you have a vertical line and you know coordinate of the top point x, first coordinate x, the second coordinate also x, right? But the second coordinate for the y gonna difference. So let's say this is y2, this is y1, then the length gonna be y2 minus y1, right? This is the well-known fact. So according to the situation here, the y2 is just equal to 1, right? Just 1. While the y1 it is on the parabola, and this parabola is x equal to y squared, which means y equal to positive square root of x. We are looking at the positive y, so this is the square root of x. So it means that the r small rx is going to be equal to 1 minus square root of x, right? And what about the larger Rx? Okay, so it's gonna be another vertical line. So let's say the top point gonna be again x1, but the lowest gonna be x, and the y coordinate now on the parabola, this parabola, which is y equal to x squared. So it means that the y coordinate is x squared. So the Rx is 1 minus x squared, right? Okay, so we identify larger radius and smaller radius for the washer. Now we can plug into the formula. Volume of washer is integrate. In this figure is from 0 to the 1, and the pi multiply larger radius square. So we have this square and smaller radius square. Okay, and then integrate dx, and then just let me move pi, and then it's gonna go to expand the square. That's gonna be 1 minus 2x squared plus x to the power 4, and then minus 1 minus 2 square root of x plus square root of x squared is x, and then integrate dx. So it's gonna be pi, and 1 cancel out. Let me integrate x to the power 4. That's gonna give x to the power 5 divided by 5, and then let me integrate negative 2x squared. That's gonna be 2x to the power 3 divided by 3, and then let me integrate minus x. So that's gonna be minus x squared over 2, and then integrate minus minus is plus 2x to x square root x gonna be 3 over 2 divided by 3 over 2. Then plugging 1 is 0. So when I plug 1, it's gonna be 1 over 5 minus 2 over 3 minus 1/2 plus 4 over 3. When you plug 0, everything gonna be 0. So the obtained number is the value of the solid. Next, let us also discuss volume of the solid obtained by revolving an axis, but now the axis of rotation gonna change to be a y-axis or a line parallel to y-axis. Okay, so it meaning that we're gonna go to take vertical y-axis to be a rotation axis, or not the y-axis, but to be a certain line parallel to the y-axis. Okay. We're gonna follow the same way as the previous case. That means we're gonna go to find cross-section area. The cross-section that perpendicular to the rotation axis. Once again, it's gonna be either a disc or a washer. For instance, in the figure here, the region is the blue region, and rotation axis is the y-axis. So when you take cross-section, okay, to the region, and you rotate the cross-section, this one gonna give a disc, right? This is a disc. But the other figure, the region is the blue region here. So, and the rotation axis is x equal to -1, which is parallel to the y-axis. When you rotate, you can see that it is a washer. There is a smaller radius for the washer and larger radius for the washer. Okay. Yeah. So our technique will be the same. So we're gonna suppose the region has y goes from C to the D. And suppose at each y, we use, if the cross-section is a disc, we're going to use the area of this a dy to be pi radius square, or washer, a area of washer at y to be pi larger radius square minus smaller radius square, and then go to integrate in the first case where the solid can be used this method. We're gonna go to integrate, not A to B, but C to D. This has to be from C to the number D, and this is from C to the D. And this is not Rx, sorry, it should be Ry, dy, and this is Ry, small ry, and dy. Okay, so let's do example. Find the volume of the solid obtained by rotating the region and bounded by x equal to 2 square root y, x equal to 0, and y equal to 9 about the y-axis. So we're gonna go to sketch the region. Okay. X equal to 0 is y-axis. Y equal to 9 is horizontal line. Let's say this is y equal to 9, and x equal to 2 square root of y is the same by taking square. Y equal to x squared over 4 with the x bigger than or equal to 0. So that's gonna be about this. Okay. Yeah, so by description it means that we have this region. The intersection for the parabola with the line y equal to 9 is intersection with x9, so it is at x equal to 6. This is the intersection point, x equal to 6 and y equal to 9. Okay, and rotation axis is y-axis. So we're gonna go to see cross section perpendicular to the y-axis. So we're gonna mark at y and look at the cross section to the region, and then follow the rotation. You're gonna see a disc, right? So we're gonna have to calculate Ry, and well, the Ry, so using the basic fact that when you have horizontal line segment and the left point gonna has the second coordinate to be equal, right? So in this case A and B gonna has the second coordinate equal to y, but the first coordinate gonna be for the left point, x equal to 0, and y for this one, it is x equal to 2 square root of y, so it means that x coordinate is 2 square root of y. Then you can calculate the Ry to be the difference of 2 square root of y minus 0. Okay, so that is the radius, and then we just go to plug. So it go from y equal to 0 to y equal to 9. So the value in this case is the disc, and integrate from 0 to the 9, and then pi times radius 2 square root of y square and dy, and this is the pi integrate 4 pi integrate 0 to the 9 of the y dy, right? So it is 4 pi multiply 9 square over 2, which is 2 times 81. This is the value. Another example, we're going to go to find the value of the solid obtained by rotating the region bounded by y squared equal to x equal to 2y about the y-axis. Okay, so first we sketch the region. X equal to y squared is parabola to the right, and x equal to 2y is a straight line passing through the origin, right? So let me draw it more better. Okay, x equal to 2y, so this is x equal to 2y. Yeah, you can see the region is just bounded by the line and the parabola here, and the intersection, you can find the intersection point to be when plug x equal to 2y, y squared equal to 2y, you're gonna give y equal to 0 and y equal to 2. Y equal to 2, and when y equal to 2, x equal to 4. Okay, so so we are going to rotate about the y-axis. So we're gonna go to take any y and then look at the cross section to the region. In this case, they're gonna be smaller radius and larger radius, right? So for the smaller radius, we're gonna go to get the coordinate. So the left endpoint is at x0 and y at y. The right endpoint at the same y, but for the x it is 2y, right? Because we are looking at the equation for this point, x has to be 2y, so y coordinate is what that's, and then you're gonna go to see the small r y to be 2y minus 0, which is 2y. And then what about the large? Okay, so the larger radius. Okay, still the left endpoint is 0y, but now the right endpoint is, well, sorry, yeah, I misunderstood. For the small radius, no, it is not on the line. It has to be on the parabola. Sorry. It has to be the point on the parabola, not on the line. Okay, to move. So it got to be on. This is x equal to y square, so it is y square, not just y square. Okay, so small ry is y square minus 0, which is y square. Now to the right endpoint, this is 2y, so the larger radius ry is 2y minus 0, which is 2y. So we know larger and smaller radius, we can go to calculate volume of washer by integrate. So this is from 0 to the 2, right? And then pi of the larger radius square minus smaller radius square. So it is y square and another square dy. And this is a pi integrate 0 to 2 and 4y square minus y to the power 4 dy. So it is pi and then 4 y to the power 3 divided by 3 minus y to the 5 divided by 5 plus 2 and 0 and do subtraction. So it's gonna go to be 403 times 8 minus 32 over 5, and that's the answer. The last example will be left as exercise.